Hi, Manish. I guess you have been joining very it's like from recently I've been seeing you are the one joining. So well, good evening, and today we're like week 8. We are just 4 weeks. Yeah, you unmuted yourself? I can't hear you actually. Okay, it's fine. So today we have this is week 8 and I'm Jagriti, a PhD student from IIT Gandhinagar. We are in the week 8 of Techniques of Material of Characterization by Professor Shubhan Roy from IIT Kharagpur. So week 7 was all about, we saw that it was mostly, wait, I'll just share my screen. So today I won't do any teaching because apparently from the discussion forum it came out that students are understanding it quite properly and assignment scores have also increased. So we have planned these 2 weeks of just looking at how you're able to interpret. So this last week was all about imaging. We saw it had different concepts of imaging. So I'll just go to that lecture here. We'll just slide through the course slides and then we can go with the assignments. Okay. So this was week 7. We did the assignment for it. And when we look at its lecture material from here, so I hope till now, all of you who will be even having a look at this lecture after some point, like probably in online when it's uploaded to YouTube, you know that from here you can be directed to Q&A and question and answers from where you'll have a chance to interact with the official course TAs. If you have some questions that you don't know how you're not able to understand them, or if you have some numerical kind of questions which are not going properly, well, till now we have tried that. Okay, units we are trying to give then with proper numbers, and we are solving them firsthand, even if the questions are being repeated from last year or some previous years. But this is the place where you can give your inputs here. Okay, so week 7 was where there were these detectors, and we looked all of them, like detectors which are used in SIM for detecting the secondary electrons, backscattered electrons. Then we had some in-lens detectors, something similar to the ones in TEM as your bright field imaging, right? Where you have direct access to the direct beam electrons. Then you have different scanning coils. Where do you have the scanning coils in different this is like they are part of the detectors. They are also part of the electron source gun, which will eventually help the beam to be focused in enough into the sample and also focused out so that your detectors will detect it appropriately. So yeah, we had a look at all of these. This ones, and then yeah, there are BSC detectors. From where do they? So in previous weeks, so these diagrams are a little bit more elaborated with respect to what we saw previously. But the diagram from week 6, which has everything, where do you see multiple layers of secondary electrons and from where the BSC comes from, where you see that interaction volume is something which is you should know, and is like the voltages, numbers. Numbers are eventually important when you are comparing one type of imaging to another. So if let's say you are comparing a scanning electron microscope to a transmission, then those things are important. Otherwise, these are like all simple components of your system that we just saw. And the imaging, yeah. So this is how actually the system looks like. So when you have this electron gun that will go into your specimen, electrons will come back. It's like which are nothing but interacting of your to your specimen, then getting scattered. So you have different detectors, and these detectors, and from where are we looking? We are looking externally out of this. We are not even looking at this. But now currently, Joel, that is JEOL, this system has made a newer upgrade, or their software has been approved to a point that you can see the electron source, you can see the gun moving, you can see the your sample moving, you can see the detector moving. So whenever you're trying to image, right? So at that point, you won't have your detector in the path. When does the detector come place? Your detector won't be actually every time perpendicular or to the sample, right? It's only the source gun which is present over there, and that only you have only one this in-lens detector. But another ones which are nothing but used for some specialized kind of imaging. You have this backscatter, you have this secondary electron. All of them are placed at an angle which the user already knows at which particular angle it would be placed, and those are like system default. default, machine default. So at that place only, when you want to do such type of specific imaging, that detector will directly zip, will come in that place and will be held over there and will you'll image it. But all of the time, your specimen, wherever your specimen is being placed, that particular area, in that area, your detectors don't even exist, because you don't want that big electron source gun to be affected, or those electrons to go by any chance into any of your detector and then harm it. Okay. The techniques and specifics of all of these we have seen: pixel size, resolution, optics, and scanning coils. Again, what's the actual use of scanning coils? Well, it helps us to focus that beam of electrons from the gun to the specimen, eventually from the objective lens. So this we have been looking at since our first week. Of course, this, based on this, we solved an example last time. So if you have a clarity of these concepts, then you can solve such questions. If not, then you'll be like, oh, this many questions. Again, this also, how it's based on the concept. So your intensity, how it's traveling with that, how our beam current, yeah, of course, intensity of the electrons or your beam current, how it's related to that of your condenser angle length. So how that's semi-angle, so it's not even a complete angle, that's like half angle, and how that particular angle is proportional to the current that you are getting through. So here, if you see, they say that the beam current decreases as the condenser length strengthens, so the ones which are below it, whereas it also decreases if the aperture is reduced. Of course, if aperture dia is reduced, current will be reduced, so the volume flow intensity which is coming through it is lesser. Okay, so accordingly like that, if you know that flow rate and times area is your velocity, so something like that. Then you have resolution analysis. Yes. So this is what we saw on that. Okay, pixel is nothing but your display size by the magnification, because magnification is something input that you're, sorry. I'll just unmute. No, silent. Huh. So magnification is something that you will input into the system, right? And then this pixel size is the displayed one, is what you eventually get after all the post processing. So how you define the size of the specimen in terms of pixels, and that to be in terms of spatial units here in microns, you do that P is equals to S by M. Okay. And after that, here was another one such thing, that if you consider that this is your total aperture width, this is your semi-angle. In this case, I guess they have, so okay, they have not semi-angle, they have taken alpha as a convergence angle, but like, okay. So alpha we usually take it as semi-angle. Here they have taken it as a full convergence angle, but convergence angle we take as theta. So conventional books, if you look at, convergence angle would be theta and alpha would be a semi-angle. Okay. So if this is an intersection plane and this is the height of your depth of focus or your plane of optimum focus, so from the area where your focus would remain eventually the same. So what it means that you don't have any diffraction related effects in particular that particular volume. Okay. So your pixel size in that case is nothing but given by h times of alpha. So h, but this is in terms of, so this is depth of field. Yeah, exactly. That region, distance of the plane of the optimum focus in which the beam diverges by no more than this particular dia, and it is limited by diffraction and aberrations, right? So in this particular case, or the region where H remains, that is the region where you don't have any diffraction, you don't have any beam related artifacts, so you always get full intensity that you want to look at, you don't have any other differences in that region, right? No losses. Exactly. And then here on base of the convergence angle they have written. So this is everything based on geometry. So here it was h is equals to, on top, if we give our depth of field over the specimen will remain in focus. So S by magnifications times this alpha. H by, oh, okay. So you have, yeah. So you have H is equals to P by alpha, right? And what was your P? Your P was S by M here. P is S by M here. And then if you do that, you get in this H is equals to S by M alpha. Okay. I hope this relationship is clear. Now, based on this particular relationship, if you look at this convergence angle, they have assumed that it's a very small angle. It's like if you say sine theta approximates to theta or cos theta approximates to theta, like that. If you take that particular distance, what's your working distance is this particular distance, and the area of the beam is this. So that's nothing but they have taken lightly sine of it. So opposite relationships, and since it's a total angle, I guess here they're saying about the semi-angle, not the total convergence angle. But okay, this two will only come in that particular case. And then totally, if you mix all of these parameters in here, you get something like this. So that's the area. Complete depth of field, or you can also call it as depth of focus. Right. So yeah, they have given that how it looks like. Importance of a larger depth of field. So, as in how you increase your working distance, your depth of field will eventually decrease because now you don't have that much region to go beyond. And then at places where you have this depth of field is higher, that means that your focus is not that sharp. That means that your electrons are not able to tightly come to a particular conjunction, and that's why is somehow also a reason to get a blurring into your image. Okay, so I hope that particular understanding is clear for all of you. And then, yeah, so ultimate resolution size, which particular resolution size you are trying to choose, will eventually depend that your beams, your image would become blurrer, or so accordingly it will give you enough sampling. So in terms of sampling, what I meant to say that your sampling is eventually based on the signal. So if you are from a signal processing background, you'll see that even every time whenever people is like, if you have two signals and if those two signals are being overlapped by each other, that means enough sampling is not being done. What meant by overlapping is that, let's say let's say I have these two signals. Okay, I hope my camera is visible. So if they are like something like this overlapping, so what I'm from here, I'm not able to distinguish the tip of this particular pen and tip of this particular pen. So what will happen eventually? I'll lose that particular information which is present in there. So for that, what I need to do, I need to sample enough number of points so that I get the distinct peaks again, right? So for that, I'll have to add more number of points in between both of them. So that is being defined by one theorem, which is like very popular. It exists. So Nyquist-Shannon's theory. What Nyquist-Shannon's theory said that minimum the sampling frequency should be twice of maximum frequency. And sometimes we also conventional amplitudes, we always do it as 4 times of maximum frequency. Well, it can be always be higher because oversampling is not an issue, but undersampling is an issue because it will cause aliasing. Eventually, aliasing will lead to removal or loss in information, right? So because of that, you sometimes lose your information and you get some blurry images. Okay. And hence your resolution will also be affected because of it, right? And yeah, this was the example I was talking about, but here also this is much more detailed. What you need to look at was the one which had secondary electrons different sizes. It's in week 6. You can always go and refer to it or just take a print out of it and stick in your room, something like that. Okay. Then, yeah, minimum attainable probe size. How much probe size should it be in SEM? So that will eventually depend on the working distance and your lens physics, is like based on the magnification what you have V by U or your focal length, and then you eventually compute the dia of it. So it said that the probe size can be decreased by increasing the strength of the lens, that is by decreasing the V1, the distance in between both of them, here this particular distance, and decreasing the working distance, right? So if your probe size is decreased, what we discussed previously also, if your working distance decreases, probe size decreases, current or amount of electrons which are coming out from there also decreases. But your strength of the condenser cell lens will now increase because it does not have enough number of electrons to pass through. So how many it has, it will force, like strongly force all of them to at one place, but those aren't even for enough for us. And as the working distance V2 increases, this particular point to the specimen, this V2 will decrease because that distance will decrease, since this value will increase, and the beam convergence angle will eventually increase. It will get more broadened. Okay. Then yeah, there are something with respect to spherical aberrations. So this is when you say that how much minimum attainable probe size do you need. Okay, so again, this is something related to field of course it's everything in optics, but now we aren't talking about optical microscope, but these are some physical principles that you should always know. So I'll just say, last time when we discussed it was that, okay, people don't remember some fundamentals, so this time I'll be giving you some brief fundamentals from there, and then you can go back, read it again, and then you can have a look at the slide. Okay. So what you see at the first point, it is written that rays which are off optic axis are subject to spherical aberrations, and instead of a point focus on the specimen. Okay, a disk of diameter forms. So what is that disk? Okay. Again, second point, we'll see that, right? And there's also an aberration introduced by diffraction at the aperture, for which electrons of wavelength lambda limits the minimum spot size. Okay. So now, whenever, let's say this is your in your microscope which is trying to see something, and this is your specimen where you're trying to receive it, and your specimen is nothing but eventually the focus of it. But that might not be the case where it is your natural focus of your electron gun, or where it achieves the maximum resolution. Okay, by maximum resolution I meant to say that at focus your pressure, intensity, pressure in terms of acoustics, intensity of electrons in terms of this particular electron microscopes, light intensity in terms of optical microscope. Okay, so when it is maximum, whatever phenomena we are looking at focus, always that particular value for that particular variable would be higher. When it is higher, it is okay, we are imaging properly. When it is lesser, it's not okay, because what happens, we'll get start having the diffraction related effects, or and any kind of artifacts, aberrations, multiple scattering, anything kind of that. Or when it is also very closer to it, that's a case where you can also affect your aperture. Now, when it is at focus, okay, it has its own resolution cell. Now, what that resolution cell is, this particular now, what do you mean by resolution? Okay, resolution is what you have the your minimum attainable capacity of your device through which you are trying to image, to distinguish or differentiate in between 2 points, right? Now, whether that is an axial or that is an lateral domain, that's fine, because it's a resolution that you're trying to define. Resolution cell is nothing but something that is defined by this particular action and lateral resolution. So this is the area of one particular kernel, that how many n number of pixels let it be in, you'll be able to differentiate if you image at that particular location. Okay. In our case, let's assume it's 2 by 2. Okay. If we assume 2 by 2, and now at focus, everything is like axial is also 2, lateral is also 2. How is axial defined? Axial is defined by the probe geometry. That's what we saw. It's like minimum attainable probe size. Now, axial resolution is something in depth. Lateral resolution is something in width. Now, as in how you go near to it, your lateral resolution is worsened. You go up above from it, it's like farther away from it, that will also worsen. At focus, it converges. Actual resolution is defined by the probe or geometrical properties, hence it's almost the same anywhere you try and look at. Above and below locations, it will also vary, but based on the sampling that you're trying to do, it will change. Okay, so but at one particular focus, at a sampling, it is fine enough for that value to be considered. But for this lateral resolution, okay, now this lateral resolution, it will eventually decrease, and then you suddenly start having the artifacts in your profile, or your images that you're trying to trick. Now, from where does this artifacts come? Only two reasons for it: diffraction and aberration, or multiple scattering. Multiple scattering is something phenomena that exists in diffraction itself. Okay, so that is the thing that you're here they are trying to say, and that lateral resolution, what I just said, is nothing but this particular formula, d subscript of d, that is nothing but 1.22 times lambda by alpha, your angle. This is exactly the same formula what we use in acoustics when I do my ultrasound kind of imaging. And that also we have the exact same formula, because all in all system imaging systems will have their specific resolution cells. If you go beyond it, you will guess these parameters. Now, in this particular case, this ds is nothing but 2 times this empirical constant, and then you have the cube of that particular convergence angle. But this formula is very important for you to consider, because this is nothing but governed by diffraction related effects, and something which causes your resolution cell to be as like when it was supposed to be a square, or when it was supposed to be a spherical or a circular resolution cell. Based on your probe geometry, it wasn't, because of certain parameters which happened because you were not at focus. Okay, so that is what that particular, so this is something which also defines your errors, or the artifacts in your images. Okay, so this is something you should always calculate before starting imaging. Of course, if it's not related to your field of interest and you just want some images, and like you just want to see how it's coming through, we can go ahead, take images, see if you're able to differentiate in between the structure. If not, try and decrease working distance in between the gun and the specimen, eventually you get a proper good resolution kind of image. But if you actually want that accurate, if you're working in a field, imaging field, then I guess you should as like give a bit of much more attention to these terms and terminologies, because this is how, if because I'm from acoustics, I'm not from optics, so but still, sorry for the noise. It's like today we have Onam celebration in our institute, so there's Chendamalam going on now, so you'll have some noises. But eventually we'll try and fund us like to stop like till 6:15 or 6:20 if possible, because this can get louder here. Yeah, so I was trying to say that this will define based on all fields, either it's acoustics or optics or it's this electron microscopy kind of systems, electron systems. You have these terms everywhere when you're trying to image. Okay, and this, yeah. Okay, so everything, all constants come from there. These formulas are not at all, it's like relevant or you shouldn't remember them. I don't know if they would be assignment or not. I haven't looked at it yet, but this is actually important. Okay. Yeah, now, as we looked previously, there were field emissions. Now, but conventionally, people were using this thermionic emission filaments. So, for this kind of thermionic emission filaments, they have previously defined the relationships kind of this. This is much more conventional to date, but if you try and understand the formula, you just see that it is dependent on the current density and the filament temperature. So, based on it, you can always remember that as in how current density decreases, that distance will also decrease. That distance is not as that particular distance. That's a probe dia that we are talking about. Okay. 2 minutes. Yeah, yes. So then they do this chemical analysis. Yeah. So based on chemical analysis, always I feel that WDS is not that important. But yeah, of course, if you're trying to do some in-depth analysis of your sample, what I meant to in-depth is nothing but some backscatter kind of imaging, then it's fine. But if you're trying to look at backscatter electron imaging, then you better go for TIM. Don't waste the resources for SIM. TIM will give you much more proper and high resolution image with respect to SIM, right? In that particular case. And then you have this EDS, where you can get the characteristic spectra. You can see that what particular element is present in this particular sample or specimen based on its X-ray intensity that is given in kilo electron volts. Okay. So yeah, there are these different systems which are there available, and from that, week 7 was done. It's like we didn't go into that much detail as we did today, but last time, yeah. So yeah, now he has shown different EDS machines, which detector is of which type. So these things, I guess you can remember. But yeah, of course, you know that which particular material you always use for semiconductors, that's silicon or germanium. So for that, it's like why? Because those are diodes which have certain cutoff thresholds from zero point 0.4 to zero point 0.7. So you take this. So there's also some kind of hardware limitations. There are some hardware advantages to us. So we use those kind of materials because of the valence band, conduction bands, electrons like that. Okay. Let me know if I'm not audible at a point, because this is getting louder now. Okay, let's do one thing. We'll look at this thing in next week, perhaps. Because what I was told was to just see your perform or like at this time the lecturers will see your performance, and then accordingly we'll see that if you want to, because this week and last week everything was more or less similar, and this is more into software. So imagery construction, more or less everything is repeating after one point. So we'll just see how is like you're able to solve this week's assignment, and then later next week we can continue with it. Okay. So I'll show you the answers today so that you understand it properly, just to help you guys throughout. Yeah. So EDS detector normally consists of what? So it is, we just saw that it has some semiconducting materials. It's either silicon or germanium. And it's because of that photon density pairs or electron valence bands, how much electron band do they have? So based on that, they have these are the ones they choose. So I don't know if I should read it out, but I guess you can. So yeah, so consequently, the number of electron hole pairs that's generated is proportional to the photon energy that's being detected. So that is why they use it. Okay, can refer to that module for it. Then, which of the following elements is not detected by EDS? So the answer is B, that's aluminum. Now, is it aluminum or something? Oh, no, no, sorry. That's boron here. Now, although the window in this is made up of beryllium or carbon. Yeah, carbon, I know. I never heard of beryllium being the SEM detector. Okay, let's say. Probably in the structure might have talked about it. And it's only few millimeters thick. It absorbs a significant amount of extra energy. So the absorption makes it especially challenging to detect the lighter elements like boron. Okay. So lighter elements cannot be detected. So if you're going to even because now you look at the range, titanium heavier, this one heavier, this one heavier. This is the lighter element. So accordingly, that won't be able to detect it. Then you have which material is used to coat the surfaces of both of them to apply a bias potential. You of course have an option of gold, but people also prefer platinum for it because of their conductive band balance. So if you need to have a proper conductivity there. Eventually, whenever you also coat your specimen is also coated for some period of time that's sputter coated with gold or the platinum. So that particular layer thickness and height is always default. Here they have written 20 nanometer layer. I don't think so if you get that specific, but uh, the system that we have in our institute, it has a timer based system. So based on this particular time, the system would be quoted accordingly that you'll get enough number of electron band balance from there. Okay. Then next is the purpose of the window in the EDS detector. What is this particular window? So it is nothing but to prevent the contamination coming from the sample specimen chamber. So that is the window that helps you. It's like for various type of specimens, you don't want that them to be burned off. So that's why you have that particular window from where your specimen can be thrown away. So this contaminants can then travel away from there and potentially won't settle onto your electrode so that your electrons are fine, and that is hence that window is designed to be transparent, intended to allow all the extra energy to pass without any obstructions. Okay, this is getting more louder now. Now, the resistivity of silicon in the detector is increased by what? So, yeah, this is more of an electronics based question. But yeah, if you dope silicon and lithium with, so what doping means? I guess till now you should know it, but if you don't know, doping is nothing but you add some impurities to your specimen. That's the exact meaning of doping. But when you consider here, let me search if I can tell you in some simple terms, doping in semiconductor. Simple understanding. Because I'm from biomedical, I've learned about semiconductors, but yeah, so you can like what this the first question gave me was that it is essentially used to increase the conductivity. Now, if we increase the conductivity, so what we are essentially doing is we want so doping means that we are adding, so if your material is pure enough, you are adding impurities to it, and that is being done here but to what do you say, to increase the conductivity. Usually that's being done. Now we want to increase the resistivity. Now if conductivity increase, that no won't work. So probably this particular elements that you have over here, so if you add some impurity into a silicon sample and your detector is of silicon itself, then probably its conductivity would be decreased and resistivity would increase. But I guess you can go and look up ahead for these elements, what happens if they are being doped. Then if you use a junction in reverse bias, so more number of current entering into it, so more resistance will increase. Or if you cool it, then it won't be conductive enough and it won't be, so it would be more resistive to it. Okay. Then, in WDS, what type of signals are permitted to reach the detector? Of course, that's nothing but your characteristics X-rays of a specific wavelength. That we know till now. And then we also saw this one thing where they were overlapped and which particular regions were they getting. Because these are of specific wavelengths, we won't be able to characterize two different ones from them. So WDS and ADS had two differences. You can always go back to previous weeks and check them again. One which was allowed for gross, complete wavelength, so full elemental wavelength, and wasn't able to differentiate one which is only for specific wavelengths. Okay. Then we had to attain the focusing effect in WDS, the crystal and detector must lie on a circle, which is known as what? So that's a Roland circle. And we also saw there was a detector with it. So that was some rose, something like that. I forgot the name of it. But yeah, this is the circle which is being called that. If you want to attain a focusing in this particular kind of system, WDS for it, wavelength based system. So the specimen and the crystal must lie on a circle for it. Why? Because let's see. The characteristic beam that's coming from the specimen is diffracted by the crystal in this. Yes, we know that. In order that as many as possible X-rays which are leaving will arrive at the detector and the geometry is chosen that all paths are focused on it. So in order to achieve this, all of them must lie on the circle of radius. That circle is being called as Rowland circle. Probably that would be a person who invented it. Okay. And we have X-ray broadening affecting the detecting efficiency is possible for, of course, which one utilizes them to image it. Okay. And then we have ninth question, which of the following statement is correct for this particular technique? So you only have a one wavelength which is detected at time for WDS, not for EDS. Then we have which one is true for these images acquired in SIM in a 8-bit pixel. Now, you can in so I guess yeah. So when you do this image processing, right? So what happens in there? I can just write it. Number of bits. How are number of bits always defined? Number of bits is eventually decided by 2 raised to n. Okay. Where did the question go? It was ninth, 10th. Yeah. Okay. I'll just try and write here. So how it's defined as 2 raised to n 0. Sorry. 0, not 0. It's decided by 2 raised to n, right? And now if you start, that's 8-bit pixel. Here n stands for bits. Sorry for the handwriting. Well, it stands for bits here. I hope you understand this one. Right. It stands for bits. So if you have an 8-bit system, 8-bit pixel, your image will have like 0 to 2 raised to n minus 1 number of pixels in it. That range will vary till 0 to n 2 raised to n minus 1. Okay, I hope that is fine. So that's why you'll get something like this, the B option here, right? Then you have this one. The grayscale value of a pixel in SIM depends on what? So grayscale value is nothing but number of detector electrons that we are detecting by the detector. Okay. Ah, it's done now. Okay. In SEM, the topographic images are obtained using what? So this is nothing but both of these, the first ones, because all other will nothing but get from deep down barrow, so those won't be utilized. So topography is something you can also get some information from some depth, but not that into depth. You cannot go beyond the morphology that you're trying to extend it. Okay. This from the specimen is capable of yielding information about what? So you'll get both the surface topography, and the compositional imaging here from backscatter imaging. Surface information you also get, but from backscatter, since you get the extra information, characteristics X-rays that are coming from specific wavelength, form specific elements, then we can also do this chemical analysis for compositional based. So that's what EDS is all about. Okay. And then what happens in when the minimum detection current to achieve a particular contrast is it will increase as okay. So this question could also be framed with respect to the probe size or probe dia. How they have defined over here is what's the minimum detection current to achieve a particular contrast level. So how much current you need so that you can get a optimum value of contrast. Okay, so that will increase when the frame time scan decreases, right? So that current that you want will increase if your frame scan time decreases. If you don't acquire enough number of frames, then you have enough time to acquire for one particular frame. So that is when the current will increase. That is more number of electrons will also come into play. So that is the thing I wanted to say is like these are kind of questions you can solve logically instead of remembering this big equations. So just remember number, what happens is like, okay, if I'm trying to use it, if my frame rate has increased, what happens if my frame rate has increased? Yeah, I'm trying to acquire more number of frames. That means my temporal resolution will increase. But eventually, what happens? My resolution temporal will increase, but my spatial resolution will decrease. That means that spatially, my resolution cell size are not enough so that I can differentiate in between 2 pixels there. So at that point, I say that, okay, that is perhaps the reason that I'm not getting enough intensity in my sample for that location, right? So that's what it means, that the current will increase when the frame time scan will increase. Okay. Then yeah, there's a question from it's like, what's the energy will this particular will rise to, and how many number of electron and electron hole pairs? So that's like we used to have in solid state. So how you solve is nothing but 10 kilo electron volts. So 10 kilo electron volt divided by this copper you take this particular potential energy level, so that's 3.8 electron volts. You keep the unit same, you eventually get the number of it. So what's the number? You divide both energies by each other, you'll get that. So for that, I guess you'll have to determine what that this characteristic value is. So you'll have to find that value if something like this is asked in some assignment. Okay. So I guess we are done with this week. If you have any further questions, you can let me know, or else I can complete for this week and then we can go ahead. Okay. What happened just now? So any questions? Yes, today not many people of you have any questions. So see. Let's see if you let's try if you can unmute yourself and see if you can speak. Do you have any questions now? Started again. Music is going on here. So yeah. Do you have any questions now? If not, then we can close up the session. If you have any question, you can let me know.
Yeah, no question.
No question. Okay, thanks for joining then. You can let me know if you have any further questions in the discussion forum. Yes, have a good weekend.
Thank you. Thank you.
Thanks for attending. I can perhaps bring the session for a while and then I can close up the session. Okay, then thanks for joining today. Bye bye. Have a good weekend.